Hey, there we go. Got a better background.
Yes, it's beautiful. Okay, so shall we start? I guess it's time to start. Good evening, everyone, ladies and gentlemen, citizens of planet Earth and beyond, visitors from other galaxies and perhaps other parallel universes. Welcome to all of you. I'm Dr. Ali Reza Rafi. You can call me Ali for short. I'm your host tonight, and on behalf of the Ottawa Intellectual Dialogue Group, I would like to welcome you all to our 20 seconds dialogue. Please be advised that we record the presentation part, and the recorded video will be available on YouTube public channel. Here's the agenda for tonight. I will have a short introduction about our group and our distinguished guest, Dr. H. Philip Stahl. We will have a 60-minute talk followed by a 30 minutes Q&A and a dialogue section about the topic. Then we'll have a 5 minutes break. We'll come back with a 20 minutes response session to some of your questions by our distinguished guest. And finally, we will have a informal conclusion. Our Ottawa Intellectual Dialogue was established by a group of Ottawa University graduate alumni in 2019. It's been around for a couple of years, and we have 15 to 20 active members from all universities in Canada, including Ottawa University, Algonquin College, York University, U of T, and so many others. We even have active members from United States who are attending and participating actively in our dialogue. And to be honest, our members come from a very diverse group of men and women from many different educational disciplines and backgrounds from all around the Milky Way galaxy. Of course, we have more science and engineering members than the other disciplines. I guess that's because there is more engineers and science lovers in the galaxy, but everyone is welcome to join our group and enjoy our monthly, sometimes bi-weekly dialogue. The main goal of this group is to provide a safe and scientific public sphere for thinking and rethinking about fundamental topics and modern subjects, as well as creating an atmosphere of dialogue. So the founder's vision can be summarized in three major headlines: to build trust, promote dialogue, and to create an environment for questions. And of course, there is no hierarchy in our dialogue. We follow the rhizomatic model in our gatherings. So feel free to ask questions during the dialogue section and make your comments. And you are welcome to get engaged about the topics. Of course, that means we promote active listening, and we are very thankful that you're attending this talk, but we encourage you to follow up with your questions and reflect on the topics. So far, we had 21 sessions in the past. Thanks to Zoom and the virtual meeting applications, we have been able to host many distinguished speakers from all around the world in many different topics. And of course, none of this would have been possible without this virtual facilities and Zoom. You can find the recorded videos for all of the past sessions on Ottawa Intellectual Dialogue YouTube channel. Of course, we rely on your support and your suggestions and your donations. So please feel free to join our Facebook, Telegram, YouTube channel. And if you would like to donate, then you can e-transfer your donation to this email, financialintellectualdialogue@gmail.com. Thank you very much again for your support and your donations. Now that I have your attention, I would like to introduce our distinguished speaker, Dr. H. Philip Stahl. Dr. Stahl is a senior optical scientist, physicist at NASA Marshall Space Flight Center. He's currently leading an effort to develop technologies for a new large telescope to replace our beloved Hubble Space Telescope. May the force be with you, Dr. Stahl. And goodbye to Hubble Space Telescope. I mean, we love Hubble Space Telescope, of course. During the last 30 years, amazing images was produced by Hubble Space Telescope, and by all means revolutionized our view about the universe. But I guess it's time for NASA and, of course, Dr. Stahl to replace HST with something better. And thank you for that. So he is technically the man responsible for developing mirror technologies for James Webb Telescope, which we are going to hear about it. But indeed, many of the world's largest telescopes have been made with the aid of this instantaneous high speed and infrared phase measuring interferometer, which was developed by him. So, and this includes technically the James Webb Telescope, the Keck Observatory, the Very Large Telescope, even our Canadian Gemini Telescope. So Dr. Stahl is technically the expert on many topics, just name it: optical engineering, optical metrology, optical fabrication, system engineering, optical testing, interferometry. He even has something with his name on it. He's the author of the Stahl parametric cost model for ground and space telescopes. He's a recipient of a NASA Distinguished Service Medal. He's a fellow of SPIE, the International Society of Optics and Photonics, where he was the president in 2014. He's a fellow of OSA, the Optical Society of America, which I believe it is called Opticon now. And he's also a member of AAS, the American Astronomical Society, and IAU, the International Astronomical Union, and so many others. Of course, he got his PhD in optical science from University of Arizona Optical Science Center in 1985. I think I was a teenager at that time. So all in all, I should say he is the go-to scientist whenever you have any problem or any issues with telescopes or optics. So, and tonight, I'm pleased and honored to have Dr. Stahl here among us, and I'm very excited to listen and to hear about the James Webb Telescope. So thank you very much, Dr. Stahl, for accepting our invitations, and you have the floor now for 60 minutes.
Great, thank you. All right, you should see the telescope. Are you seeing it? Okay.
Yes.
Yes, we are seeing it.
All right, so let's see here. Well, I am presenting. I'm not going to probably be able to see the chat, but let me see if I can modify my screen a little bit here. All right, I think I'll be able to monitor chat. So if I see a question in the chat, I'll endeavor to answer it. And but it's hard to multitask. Okay, so thank you for the invitation to speak with you tonight, and the kind introduction. I guess I need to hire you as my publicist here. And so we call Webb the first light machine because that's its primary science goal, is to look for the first light of the universe. And with NASA, what it is that everything that we do at NASA is driven by questions. And these are the three questions we have that we're dealing with in the astrophysics division. How do we get here? Where are we going? And are we alone? And so Webb is designed to address some of these questions. We start with the Big Bang. We're going to go through the region of the first light and the time of reionization, galaxy formation and evolution, star formation and planet formation, and try to look for some life. And Webb's got the mission objectives is to study like I said, the origins, the evolution of galaxies, stars, and planetary systems. It's a near-infrared optical to near-infrared telescope. It starts in the visible at 0.6 microns, goes out 28 microns. It's required to have a 5-year mission life with a 10-year goal. And now that we're on orbit, we're predicting 15 to 20 years, is that the European launch vehicle was so efficient in getting us out to the Sun-Earth L2. And we didn't have to use very much propellant. Plus, because we were delayed we got a gravity assist from the moon. So we have enough propellant for probably at least 20 years or maybe longer. The mission was managed out of Goddard Space Flight Center in Baltimore, in Greenbelt, Maryland. We have a collaboration from the Canadians who provided the guider system. The Europeans contributed some of the instruments. Prime contractor was Northrop Grumman, and there's the list of the instruments. The near-infrared camera was out of University of Arizona. Near-infrared spectrometer out of ESA. Mid-infrared instrument from JPL and ESA. And as I said, the fine guidance sensor was from Canada, and it's operated out of the Space Telescope Institute in Johns Hopkins University in Baltimore, Maryland. So one of the questions, Webb costs a lot of money, and it's because it's very hard. And so the question is, why was it so hard? It is, first off, it's a big telescope, and our current launch vehicles are only 5-meter fairing. So how do you put a 6.5-meter telescope into a 5-meter fairing? Well, you have to fold it up, and so that causes it to be difficult. Its science is it requires an infrared telescope, and as an infrared telescope, it has to operate at a very cold temperature of below 50 Kelvin. It's it's not a temperature that we make things at on the ground very easily, so we have to do special test configurations and take it cold into cryogenic temperatures to characterize its performance. And in general, anything in space is harder to do than something on the ground. And the reason we go to space is because the atmosphere doesn't transmit in the wavelengths of the area we want to do science. And so, the visible region of the atmosphere is clear, but with Webb, we're starting at the red air and going out here out to 20, 30 microns. So you can see there are regions in the atmosphere where it's quite opaque. And so we have to get above the atmosphere in order to be able to do the science because it's an infrared telescope. And so for those that may not be technical, what is infrared light? Infrared light is just heat. And so when you stick your sun out into a sunbeam and you feel the warmth of the sun, or you put your hand near a fire and you feel the warmth, that's your hand is being irradiated by infrared radiation. It's being illuminated by infrared radiation. And the other question is, why do we want infrared? So this is a very famous Hubble picture. It's called the Pillars of Creation, and it was taken in 1995. And this is what it looks like with the This is what it looks like if you take the Spitzer telescope. And so when you see the Spitzer compared to Hubble, you can't see inside all the dust. But once you get to Spitzer, what you can now see is that you can see these are star forming regions here on the areas. So we want to be able to look through the dust to see what's going on. And this gives you an idea how big Webb is. It's a 6.5-meter primary mirror. The sunshade is about the size of a tennis court, or maybe bigger than a pickle court. And like I said, we have to fold it up to get it inside of the launch vehicle. And then once it's on orbit, it unfolds. The telescope has a cold, the entire payload, there's a cold side and a warm side. The telescope is on the cold side and the spacecraft is on the warm side. And we have a sunshade that keeps the separation between them. And we are launched to the Sun Earth L2 point, which is about 1.5 million kilometers away from the Earth, which is a little over 3 times as far away from the Earth as the Moon is. And this is a gravitationally stable orbit. Is that the gravitational pull of the Sun and Earth combined matches the centripetal force that wants to throw the telescope out of the orbit. And so the whole thing orbits around the sun. This is called the Sun Earth L point number 2. There's the number 1, which is between the Earth and the sun, where the gravitational pull of the Earth and the sun balance each other. There's a 3 and a 4, a 4 and a 5. 3 is on the other side of the sun, not very useful because we can't talk to it. And so here's a little animation that shows the how the telescope is orbiting the sun along with the Earth. And so the telescope requirements has got 25 square meters of collecting area. It's a 2 micron diffraction limit of specification operating at below 50 Kelvin. We had a goal of trying to get to 25 kilograms per meter squared, cost of 6 million per square meter. These are the goals. And there's 18 rings in a segment. Each one of these segments is a 1.3 meters flat to flat with a 20 nanometer RMS surface figure air. And so the way to think about that is here in Canada is that if you scaled up one of these mirrors to the size of Canada, um, the Rocky Mountains or the Canadian Rockies would not be any taller than an orange. So it's a very smooth mirror, and it's specified that the low order figure air is going to be about 4 nanometers. Figure air mid spatial frequencies about 18 or 7, and the micro roughness is about less than 4 nanometers RMS. And another example is 20 nanometers RMS. You know, a typical human hair is something on the order of 100 microns. And so this is a hair versus 20 nanometers. So it's a very smooth mirror. This chart illustrates, compresses, if you will, 6 years of my life into one chart. So when I joined NASA in 1999, the goal was to get the mirrors to an areal density somewhere down here around 20 kilograms per meter squared. The uh, the Hubble Space Telescope had been up here around 240 kilograms per meter squared. There were some technology demonstrators that were in the 60 to 100, 60 kilogram per meter squared. The Spitzer telescope was about 30. And so that was our goal. And based upon lessons that we learned from running prior telescopes, we wanted to get our TRL to TRL 6 before the non-advocate review, the NAR. And so for those of you that are in academia, you've been through grad school, the non-advocate review is sort of like a qualifier exam or a preliminary exam before you can enter into your PhD program. Is that it's a bunch of people who don't have a vested interest in the mission that will decide whether or not you can go forward with the mission. And so we started spending money in 1996 with a little half-meter subscale beryllium mirror demonstrator that was a sphere. And then we went through the advanced mirror system demonstration phase, where we funded a phase 1 with 5 vendors, and it looked at 8 different concepts. Then we down selected to 4 concepts with 3 vendors in phase 2. And then we eliminated one of the vendors, and we carried 2 concepts all the way through to a fly off, if you will, at the end of the program. And so for those of you that might become program managers someday, this is actually a very efficient way to manage a program. It may seem like you're spending money you don't need to spend, but competition motivates people to do their best work, and competition motivates people to keep their costs under control. And we saved so much money and we learned so many lessons by running the competition that it paid for itself. So after we've selected a prime contractor, we selected the beryllium mirror as our baseline, and then we built an engineering development unit to do TRL level testing, to vibe and acoustic test the mirror to bring it up to TRL level 6. TRL is NASA speak for technology readiness level. Something that is a drawing on a napkin is considered TRL level 1. Something that is flying in space is considered TRL level 9. Something that's been demonstrated as a prototype in a laboratory environment is considered TRL level 3. Something that is considered ready to flight, that has been validated at scale, demonstrated in a relevant environment, which is, a cryogenic environment, a thermal environment, has been vibrationally tested, acoustic. Anything ready for flight is considered TRL level 6. So we got to TRL level 6 in about 2005, 2006 timeframe. And one of the things we did with all of these mirrors, every one of these mirrors, we brought them through a NASA Marshall, where we cryo tested them in this giant vacuum chamber down to 30 Kelvin. We could test 6 mirrors at a time. Here's just some pretty pictures of some mirror testing. And as I said, we took them down to 25 Kelvin as a survival temperature and then brought them back up to about 45 Kelvin to measure their shapes. And by measuring the change in the shape of the mirror between room temperature and the cryogenic temperature, we created hit maps, which we then measured. We measured the change in the shape and then polished that into the mirror, so that when the mirror was on orbit at the right temperature, it would have the right shape. And so here's what the final estimate of the mirror shape was before we coded it. Is about 20. We had a requirement of 25 nanometers. We made it to 23. There was two mirrors where there was a math error in the hit map, and we actually polished in the air instead of taking the air out. So we doubled the air, but we had enough reserve that it wasn't a problem. Then all the mirrors were coated in gold, and the specification for the gold coating as a function of wavelength is given by this red staircase, and this data is the measured reflectivity of the mirrors. So all the mirrors are shinier, more reflective than they were required to be. Then you take and we put the whole thing together. So this is the assembled telescope that was assembled at Goddard. This is the spacecraft and the sunshade, and they're going to get integrated together at Northrop Grumman. And one of the things we did is once they were at Northrop Grumman, is we tested them all. And let's see, there we go. We tested every single motion. So we would fold up and unfold the telescope. We'd fold up and unfold the secondary mirror structure. We would unfold and deploy and spread out the sunshade and put it back and do it. And so we tested every single possible motion of the system before we then packaged the whole thing up and buttoned it up for launch. We'll let the sunshade here finish. There, I think the sunshade's done. And then we put it on a big boat. It took it through the Panama Canal down to French Guiana in South America, close to the equator, and launched it. Beautiful launch. And then here's the last picture that we have of it before it was deployed from the rocket and on its way out to CERN Earth L2. And this is what it would go through. So the first thing we got to do is got to get the solar panels out because batteries don't last very long in space. We got to get electricity. Then we have to establish communications. So we got to get the antenna to be deployed so we can talk to the spacecraft from the ground. And then we got to open up the sunshades. And once the sunshades are open, we push the telescope up away from the sunshade so it can start cooling. That's the kite tail. The kite tail is really important, just like a real kite tail. It helps this telescope. Think about it as it's a giant kite, and it's going to fly on the solar winds, and that tail helps to stabilize the kite on the solar wind. And each layer of the sunshade drops the temperature of the telescope by about 50 degrees Kelvin. So one side is going to be at 300 K and the other side is going to be about 50 K. There's 5 layers. And then once you get it, we got it deployed and in orbit, we have to phase the segmented mirrors to get them to work. You know, they could have discontinuities, but they're all actuated. We have hexapod actuation under, and we can move them up, front, back, and around, and tip them and tilt them. And so the first thing we have to do is figure out where each segment is. And so we just look at a star and we look at the images, and then we find the spots, and then we bring them all together on top of each other. And so when we opened it up, you know, we found the spots, and there's the wing spots, and there's the center spots. And this is the first time that we could see a star image from all 4 of the 18 segments. And then we have to position them. And you'll see that, you know, some of the segments are in better focus than other segments. And so then what we do is we then have to adjust the focus on each segment. And then when we stack them all up, we get this pattern of the stacked image with diffraction spikes, and then we phase the whole thing, and uh, and then we take a shot an image. So this was the first official image out of the telescope. This was an alignment verification image, and some of the things to note is that you can see we have very nice diffraction pattern. And actually, I'll back up. This says you have a very nice diffraction pattern. Therefore, that means all the segments are aligned with each other and they're phased. And then here, this was a diffraction. Now, this was a completely generic, boring star. It was supposed to be just a single star. And when it came up, we had all this stuff in the background. But here's what I saw as an engineer, as an optical person. I saw every single star in the image, no matter where it was, looked like it was a really nice clean diffraction pattern, which tells me that the telescope is properly focused over its entire field of view. That's really important. The other thing is there's lots of stuff in the background we didn't expect to see. That means this telescope's really sensitive. There's galaxies there that you can see, galaxies there and there. So the very first image of this telescope, it showed enormous promise. So these are the four science instruments that operate. There's a near-infrared camera, and it's going to image. It provides the images. The near-infrared spectrometer is going to it gets spectra of hundreds of galaxies at a time. The mid-infrared camera takes images in the mid-infrared, and then, of course, then the fine guidance sensor provided from the Canadians, and the pointing of Webb is absolutely exquisite. It also has some more imaging in there and a coronagraph instrument. And each of the science instruments is mapped to a different place in the focal plane. So this curve, the image plane of Webb is curved. It's because it's a 3-mirror anastigmat, in that the part of the image that is the absolute closest to the optical axis is up here. The part of the image that's the absolute closest to the optical axis is the highest quality. That's where the best imaging is, and that's why this is where the near infrared camera is located down here. The fine guidance sensor is actually up at the edge for a very good reason. Is that star trackers actually like their objects to be a little bit out of focus. The mid-infrared camera is in this region, and spectrometers can be a little bit further out because spectrometers are not, as being non-imaging, they don't require the wavefront quality to be as good. And again, this slitless spectrometer here is actually part of the fine guidance sensor. And so here's again from the engineering units that this was taken. This was just the telescope was pointed, I think, at the large Magellanic Cloud, which is a region in space with lots and lots and lots of stars. So the telescope was just pointed at this, and data was taken for each of the science instruments. And again, what you need to note is that everything is in focus. Every single science instrument is in perfect focus. There's a star in every single instrument, and they're all beautiful. The other thing it turns out is that we designed this telescope to be 2.5 micron diffraction limited performance. It's actually performing at 1 micron diffraction limit. This telescope at the same wavelength as Hubble performs better than Hubble. It just performs at different wavelengths than Hubble. So these are the design specs as if it was a 2 micron telescope. So you can see, and here's the field of view. So the field of view of Webb, 130 by 160 milliarc seconds, is bigger than Hubble's field of view, statement number one. At 2 microns, it was 0.06. Hubble's uh, 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 resolution at 1.6 microns was 0.14. So this is really going at 0.03. So it's 4 or 5 times. It's probably performing 5 times better than Hubble. Its larger aperture gives us 6 times more sensitivity than Hubble. The Spitzer, its larger aperture, gives its 44 times more sensitivity, and it's performing about 14 times its resolution is about 14 better than Spitzer. So this down here shows the wavelength coverage. Hubble goes from the ultraviolet zero point 0.1 nanometers all the way out to about 2.5 microns. Spitzer goes from about 5.5 microns out to about 150 microns, and Webb is covering this region between the two. So this is a comparison of how Spitzer performs with Webb at this is 8 micron wavelength on Spitzer. It's 3 arc seconds. This is Webb's performance at about 7.7 microns, a 1/4 arc second. So again, almost 13 times sharper than what you can see with Spitzer. And this is a comparison of what you see with Hubble versus Webb. Now, one of the things to note is Hubble has a cross spider for the secondary mirror, so that's why its diffraction patterns look to be like X pattern, whereas Webb's diffraction pattern is looking, what you're seeing is the hexagonal shape of the aperture. The other thing is you can see there's a lot of fuzz and blurring, if you will, around the Hubble images that's not there with Webb. And again, so when we tested the mirror on the ground, this is what we tested the mirror to be, predicted the primary mirror to be about 20 nanometers RMS. The on-orbit performance is really about 20 nanometers RMS, and the difference between the two after a couple of micrometeoroids impact is a 17.5 nanometers RMS. And we've had a couple of good-sized micrometeoroid impacts, but they haven't had a huge impact. And it'll be years before the performance of this telescope is degraded because of the micrometeoroids. All right, so that's the engineering aspects of the telescope. And now I'm going to spend about a half an hour talking about science. And so the first science theme of the Webb telescope is the end of the dark ages, first light of the universe. And so after the Big Bang, the universe was a bunch of quarks and leptons and things like that, and then they became into electrons and protons, and then they produced hydrogen atoms. And when we do with our telescopes is that the bigger the telescope, the further back we can look, the further back we look. So the cosmic microwave background telescopes, they look at this region back here, this ionization region. Hubble is looking in the visible. Webb is designed to look at this region of the cosmic dark, this boundary, if you will, what's going on at this time in the universe. And the way we do this is so the very early universe was made up of clouds of neutral hydrogen. And so as gravity pulls this hydrogen together, the first stars are born. And as they form, what they do is they start to clear up bubbles in this neutral hydrogen until they consume all of the neutral hydrogen, and the universe becomes ionized. The universe becomes transparent because you cannot propagate light without ions. And so we had to clear out all the neutral material, make the universe ionized in order to become transparent. And so the way we study this is what we do is we look at the redshift. Now I'll talk about redshift in a few minutes, but the whole idea is that we're going to use spectroscopy, and that when we look at an object, if we can see its full spectrum, then it's in a fully transparent universe. But if we see dropout in the spectrum, then this patchy. It's in this region of foam where the universe is partially transparent and partially opaque. And if we can't see anything but maybe a single line, that means it's a very early object inside the universe. And what redshift is that the further away something is, the redder it is. So if you can see something in the blue, it's pretty close. If you can't see it, it's in the red. And the region is that the universe is expanding. So this is a little graphic, is that the idea is that when this light was emitted from this star or this galaxy, you know, billions of years ago, the universe was smaller. But as the universe gets older, the universe stretches, it expands, and as it expands, the space is stretching, and so it is actually the stretching of space that is causing the light to stretch out and shifting it from blue. And so here's what we look at is that this is the Fraunhofer absorption pattern of our star, our sun, and you can see a close by galaxy has similar absorption lines, but the further away you go, the more these absorption lines get shifted into the infrared. And so this gives us a meter stick for measuring time and distance. And so this is a very deep image of the Hubble Deep Field. So this is a star that was not seen in the visible, in the blue or the green or the red, but was seen in the 1.6 micron wavelength band. And so this object is very red and it's very old, about 480 million years after the Big Bang. This is considered a Z of 10. Here is something from the Webb early release data. This was the data that was released on day one, July this summer. And this is based upon a 12-hour exposure. This is a 2 by 2 arc minute view of the sky, which makes up, and this is a small number, but basically that is 2.7 millionths percent of the sky. Um, and there was one star in here that was found that or actually it's a galaxy about 13.1 billion years old. We did a spectra on it. It's got oxygen and neon and hydrogen, and that's just amazing. And this is what the near infrared image looked like of that sky. And here's the mid infrared image. And then over the course of the next few weeks, this collaboration group out of Scotland, they took 690 individual images and they stitched them together, and they found that little star right there, which is up in here. There it is, right there. They named it after the project lead head's daughter, Maisie. It's a redshift of 14, 290 million years after the Big Bang. One of the things, so galaxies form. The universe is made up of this cosmic web of filaments of hydrogen gas that are flowing through the universe, surrounded by dark matter. So the dark matter sort of keeps them into their channels. And wherever these galaxies kind of cross over, that's where we have that's where wherever these rivers of hydrogen gas cross over, that's where the galaxies form. And so, here's examples of galaxies forming, and here's some data that was taken of a couple of galaxies forming up. And so, one of the things we're going to study is these early galaxies. And one of the reason I have this slide up is that this is a Hubble galaxy that's redshift of 11. But one of the things is that when it's compared with Spitzer, is that it's generating stars. It's making stars 1,000 times faster than a modern galaxy is. It's 25% smaller than our own Milky Way, but it's producing stars, making stars that are 20 times faster than our Milky Way. So these early universes, and Spitzer sees the same thing, is that these early universes are very hot. They're very bright. These early galaxies are generating lots and lots and lots of stars, lots and lots of ionizing radiation. So this is the Hubble Deep Field. This was a very famous image that was taken on early on in Hubble, acquired over 173,000 exposures over 4 days. And inside of there are 47 galaxies that are somewhere in the 600, 650 million years after the Big Bang. If we look at the same field with Hubble, we'll probably, or with Webb, we're going to see incredibly a lot more and a lot deeper. But when we looked at this with Chandra, um, every one of those ancient galaxies had a black hole in the middle of it, which raises the question: what comes first, the chicken or the egg? What comes first, the galaxy or the black hole? And these are all, really ancient galaxies. And some of the most energetic X-rays are detected indicate that these black holes inside these young galaxies are pretty good size, and they're really eating lots and lots of gas. And One theory is that a galaxy forms at one of these cross sections between the rivers of the hydrogen, and it spins up, and gravity collapses, and as it collapses, the black hole forms. Um, Another theory is that these black holes are called primordial black holes, and that they're leftover bits and pieces of the Big Bang that never expanded. It's bits and pieces of the early universe that never actually became ionized and never expanded to the point that it became matter, and they just sort of collapse back down, and then they pull all of this mass and gas back around them. One of the things you need to understand about first light stars is that they're 100% hydrogen, and they're going to be huge, 1,000 times bigger than our own. And because they are just so big, they don't last very long. They're unstable, and they explode into supernova. And so that's one of the things that we're going to look for within Hubble or with Webb is these stars exploding into supernova. And the other thing is that when we take spectra of these stars, the first stars, when we do the spectra, we should only see hydrogen spectra, nothing else. But after they explode, in the process of exploding, they make other materials like helium. So the second generation stars have helium, and our star actually has a lot of iron in it. And so here's another possible explanation for black holes is that this is a star that's about 20 times the size of our own sun, and it was there one day in 2007, and it wasn't there in 2015. It just disappeared. Well, how could that be? It didn't blow up. We would have seen it if it blew up. So it must have possibly collapsed into a black hole. Even if it was a neutron star or a white dwarf, we would see it. But the fact that we don't see anything indicates that it just collapsed directly into a black hole. So some of these earliest stars may, instead of exploding, they may collapse directly into black holes. And so here's an example of a very early black hole. I think it's this red dot here in the image is where we're putting it. And there's probably a very dusty cloud here. And it's about 750 million years after the Big Bang. And it's a very big black hole. All right, so science theme number 2 is how do galaxies assemble? And so when we look at early galaxies, all of these early galaxies are kind of simple because they're young, but they're also really blue because they're generating a lot of stars. They're very hot. So that's one of the things we're looking at. And then the question is that how do mature galaxies form? There's spiral galaxies and barred spirals and ellipticals, and so how do we get to our shapes of our modern galaxies? And so one of the ways to look at it is we have collisions between galaxies. And so here's some really ancient collisions of data that's taken with Hubble and Spitzer and Keck and ALMA. And the idea is that as these things start to spin up around each other, we'll look at the light. And so back to back, this is the redshift that's similar to the siren effect, whereas noise source that, or the Doppler effect, is that a noise source that's coming towards you has a higher pitch, and a noise source going away from you has a lower pitch. Well, the same Doppler effect applies to light. Is that if the light source is moving towards you, it's going to be upshifted and it's going to look blue. If the light source is moving away from you, it's going to be downshifted into the red. And so now we can look at the Doppler effect of light around these galaxies and see how they're spinning. And in fact, here are some results from Webb that was published this week, I think, is that this is a 3 galaxies spinning around a supermassive black hole, and you can see at different wavelengths, different parts of these 3 galaxies start to light up, and you can see very clearly that some are moving away from us and some are moving towards us because of the Doppler effect of light. And then, of course, then things collide. And so we're interested in how things collide and form. And one of the things that's interesting is that when things collide, they don't generate a lot of heat. Is that galaxies are actually mostly empty space, and so they kind of just move through each other. And one galaxy will maybe strip off things from the other galaxies and planets and dark matter. And in this case, what we have two black holes. These are up this corner here is two black holes that are orbiting each other, and they're eventually going to collapse into a single black hole, and it'll be a very huge event that we'll see with the LIGO measurement device and the LISA experiment. This is a famous. This is again some early, Webb early release data. This is called Stephan's quintet. This is the Webb data taken. This is the Hubble taken with the Wide Field Camera 3. And these are, it's really interesting. This is the near infrared result. This is the mid infrared result. You can see in the mid infrared, you can see where all the gases are distributed. You can see kind of the structure of these objects. And then of course, then they did some spectroscopy. And one of the things used that, so they went down into the middle of this galaxy. So right here in the very center of this galaxy where the black hole is, you can look and you're seeing hydrogen, silicates, that's basically sand. And then also, here's neon and sulfur showing up. So different materials. And this is actually out here in the further zone. And this is a comparison of what these images are with Hubble versus Webb. So again, Carl Sagan famously said, "We are all stardust." Is that every element in the universe was made in a supernova explosion of a star? And in fact, so we talk about second generation stars. They're going to be, first generation stars is 100% hydrogen. Second generation stars have got mostly helium and a little bit of heavier elements. In that, if as material gets cycled through stars over and over and over again, you get more and more iron. And that, our own star is a very mature star. It's got iron in it. And that when you think about our planetary system, our planet cannot have an element that does not exist in our sun. So our sun is responsible for everything that is on our planet. And so this is a Subaru deep field, and there's just 150 supernovae, 22 of which are 10% of just the Subaru deep field. They're these supernova about 4 billion years after the Big Bang. And what they're saying is with this data, what we can see from the ground, supernovae are about 10 times more frequent than they are today. My guess is that my expectation is that when we go back and we look much, much closer to the Big Bang, we're going to find supernovae 100 times, 1,000 times more frequent than today. Birth of planetary stars and planetary systems is theme number 3. So again, I showed this image earlier. This is the pillars of creation where we have star formation on the tips this week. So here is the Eagle Nebulae taken in 1995 on Hubble. And here's what was released today on Webb. And just a gorgeous image. And there's new star forming regions. There's some red areas here, and red stars. There's a whole bunch of previously unobserved stars that we're seeing in this data. So if Hubble and Webb have seen the pillars of creation, Spitzer found the mountains of creation, and this region is actually right in here. So this gives you an idea of scale. And every one of these green boxes is a star that was created, that was formed from this dust. And over here, all of these green boxes are really, really young stars. And so what's happening is all these stars off the coast, if you will, the solar wind is blowing onto this pile of dust and compressing it at supersonic speeds, which heats it up to form the stars. So here's an example: is that here's a star over here, and its solar wind is blowing through this dust region at 24 kilometers per second and just compressing it supersonically. Herschel has found lots of examples of star-forming regions inside the Ego Nebulae. So here's a star is clearing out a zone of dust around it. Here's another one over here that's clearing out a zone of dust around it, and in the process, it's feeding, say, this star down here. Well, Webb has found the same thing. There are lots and lots of little bubbles in this data that you can see. So this is the Corona Nebula over here, and this little triangular box is this big box that's being imaged by Webb. And then this little region over here shows up here, and then there's a bit piece there. And what you can see is you can see the shock front of the compression of the dust that's going down to start the form. So this is the near infrared image above, and this is the near infrared image combined with the mid infrared image down below. And this is a comparison of what Hubble and Webb saw when it looked at the same region. You can clearly see that Webb has much more detail than what Hubble can show. Um, this is back to some Herschel data. This is back to the Ego Nebulae. Again, you can see lots and lots of little pockets that are getting cleared out by stars. The younger stars are the blue. Blue is hot, and the other thing is that Herschel did spectroscopy on the Ego Nebulae, and all the ingredients for life are inside this nebulae. There's formaldehyde and methanol and water and sulfur dioxide, carbon monoxide, everything you need. All right, so science theme number 4 is planetary systems in the search for origin of life. There's different theories on how planetary systems form. There's the accretion model and there's gas collapse model. So the gas collapse model is that as planet seeds circle around the star, that it collects gas and it builds up a planet by making a snowball that's, you're rolling around a yard. The accretion model is that you have clumps of material that bump into each other and stick together. And as they stick together, the mass builds up and the gravity, and then they pull other clumps of material to them and they gather together. And what do we know about planetary systems? Well, oops. So what we know is, we have planets, and then as we start discovering asteroids, and we discover there's more and more and more stuff. And so what we learn is that our own planetary system is basically clouds of dust. And then the accretion model is verified by the New Horizons when it flew by Ultima Thule. This is what Ultima Thule looked like, and it's made up of lots and lots of chunks of different kinds of material that we can determine based upon spectroscopy. And so the accretion model seems to be the right model. And then planetary disks form out of stars. Stars make planetary systems. So this is an example inside of the nebulae, the Orion Nebulae Hubble imaged. And each one of these is a protoplanetary system being formed. And here are some examples of protoplanetary systems that are imaged with the ALMA from the ground. And there's spirals and there's rings and there's lots of different ways in which to look at planetary systems. So planetary systems are ubiquitous. And the other thing is these are all dust. What we're seeing is the dust. You can't have a planetary system without the dust. You have to look for the dust. Um, One of the key things to understand about planetary systems is the habitable zone. And the habitable zone is where liquid water exists. And some people like to call this the Goldilocks zone. It's not too hot, it's not too cold. If it was too hot, you'd have steam. If it was too cold, you would have ice. And you have to have, for life, you have to have liquid water. The other thing is that our sun is a G-class star, and so its habitable zone is in this zone right here. Hotter stars, their habitable zone is further out. Cooler stars, M-class stars, their habitable zone is further in. Now, one problem with there's a lots and lots and lots of M-class stars in the galaxy, more so even than G-class stars. So that would imply that we want to study M-class stars. But the problem with M-class stars is that they are active. They have lots and lots of sort of solar flares. There's a lot of radiation coming off them, and because the habitable zone is in close to the star, basically these stars are going to sterilize whatever is growing on their planets on a regular basis. So where does the water come from? Um, this is some spectrum of Spitzer, and basically it comes from the star. The star is like a fountain. It makes water. And so this is a spectrum taken of a protoplanetary system, is that the star out of its poles is shooting water vapor out of the top and bottom of the poles until it gets far enough out of away from the star that it cools down. It condenses onto dust and then falls back down onto the planetary system as snow. And it does this not only for water vapor, it does this for carbon dioxide vapor, it does this for methane vapor, and so all of these different vapors are shooting out of the star like a giant fountain, condensing on dust and falling back down into the planetary system. And so there's these snow lines, is that as you get a certain distance away from the star, that's where a snow line forms based upon a given temperature. And there are different snow lines for different materials. There's a water snow line, there's a methane snow line, there's a carbon dioxide snow line, and that determines what the different planets are made up of as where the snow line falls. And so one of the things we need to do is that we have to, each different regions of this planetary disk requires us to study at different wavelengths. And so the Webb is going to study this gaseous phase to the into the near infrared, whereas we would need a far infrared, mid infrared to far infrared telescope to study what's going on further out away from the star. And there's different ways, there's different kinds of stars. There's hot lava worlds that are really close into their star. Hot Jupiter's really big star. So this is a plot of small planets, big planets, planets that are close to their star and very hot, planets that are far away from their star and very cold. And so, and this is the orbit. So this green line is about what our planet is located. That's where we'd be wanting to look for. So there's different ways to find stars. This is the radial velocity method, or to find planets. So this is a method whereby a planet, as it's orbiting its own star, causes that star to shift relative to us. And so using the Doppler effect that we discussed earlier, the sunlight gets shifted red and blue and red and blue. And so what we're looking for is we're looking for a wobble signature in the spectrum of the light coming off this system. And the bigger the planet is, the bigger the wobble. The closer that planet is to its sun, the bigger the wobble. And so the first exoplanet, Peg 51 Pegasus, was discovered in 1995 using this method. And since then, we found lots and lots of other planets. Here's an example of 61 Ver with 3 planets inside of an orbit about the size of Venus. Again, the radial velocity method works best for things that are close. The next method is the transit method. This is the method we use with the TESS experiment. And so what we do is we stare at a sun or a star and we look for dips in its light curve. So when a planet passes between our telescope and its star, that planet blocks some of the light. And by measuring the dip in the amount of light that gets blocked, we can estimate the size of the planet that's passing in front of the sun. So here's some example of a real live light curve dip, and it's a really, really small dip. It's just a small fraction. And Kepler found over 1,000 confirmed planets and maybe 4,000 confirmed stars. And one of the first multiple zone planets that Kepler found is Kepler 22b. This is this is say a Mars orbit here. Actually, this is the first. This is the first planet that Kepler found as a single planet. Its orbit is something on the order of the same as Earth, and it's about 2.5 times the size of Earth, and maybe it's got about the same temperature as Earth. Spitzer actually then found the TRAPPIST system, which is an M-class star, and I talked about the M-class stars being environmentally unfriendly, but it's got the TRAPPIST system has got I forget 1, 2, 3, 4, 5, 6, 7, yeah, 7 stars that are within an orbit way in here. Okay, so they're very close to their sun, much closer than Mercury, but they're all about the same size as our own planets. And this is how the Spitzer used the transit method to find its star. And so this is the data stream from the Spitzer for finding TRAPPIST. And what it is that you look at the periodicity of the signal, and then you do a Fourier analysis to figure out the frequency of each of these signatures. And one of the things, the reason it's called TRAPPIST is that this experiment was being run by a group out of the Netherlands, and so they named it the TRAPPIST system in honor of the Trappist monks and their beer, which they use to celebrate. There's a way that you can actually get spectra from transit data. As the planet moves between the star and the telescope, you can see absorption lines from the atmosphere of the planet. So we can actually look at the absorption that occurs in the starlight in order to figure out what is in the makeup of the planet's atmospheres. And so this is some Webb data. This is Webb data of a transmission spectra through an occulting experiment where the planet's moving in front of its star for WASP 96b. It's a very large, puffy giant, about 1.2 times bigger than Jupiter, and it has water. So there's spectra of water right there and carbon dioxide. And this is part of the first release data. Here's some more pretty pictures of, this is Webb data of Jupiter that shows the clouds and the haze. This is the near infrared image, and this is the mid infrared image combined with the near infrared image. It shows where you can see the auroras, the northern aurora and the southern aurora. You can see that Jupiter actually has a ring, which is probably made up of a decomposed planet. And you can see another couple of planets. And then there's Neptune. And you can see Neptune has a very complicated ring. It's got a couple of moons inside of its ring. There are seven actual moons in this system, including Triton. And I think this object right here is actually Triton. It's Neptune's large moon. So exoplanets, as of March of 2022, we had confirmed about 5,000 total exoplanets through all these different methods. We have 30% of them are giant gas-like planets like Jupiter or Saturn. 30% of them are super Earths, which are something between Earth and Neptune. Maybe 4% of them are terrestrial, like our own rocky Earth. 35% are Neptune-like planets. And so this is some Kepler data, 2017, is that there was over 100 planets that are within 2 Earth radii of our own, 2 times the size of our own planet, 25 of which are those that are in the habitable zone of their particular star. We have 100 or so habitable planets, Earth-like sized planets in the habitable zone, of which 25 are smaller than 2 Earth radii. But it's important is that it's not just being in the habitable zone, but it depends upon where you're at relative to the star. Is that if this is the starlight relative to sunlight on the Earth, is that if you have too much light, you get to carbon monoxide toxicity. You don't actually, this is 0.5. If you don't have enough energy, if you don't have enough sunlight coming in into the atmosphere of the planet, you cannot clear out the carbon monoxide. And if you don't have enough energy coming in at these wavelengths up here, you cannot clear out the carbon dioxide. So you have to have your planet close enough to the star that you get enough energy onto it that that you have a mostly oxygen nitrogen environment, and you don't have buildup of carbon dioxide and carbon monoxide. And then and what you find when we look at all the statistics, we find that about every single star in our galaxy has 1 to 3 planets in our habitable zone. Our own star has Venus, Earth, and Mars technically in the habitable zone. And so there are 17 billion stars in our galaxy that are like ours, class G stars. So potentially there could be 17 billion Earth-sized planets in our own galaxy. The question is, how many of those planets are then in the habitable zone? And more importantly, how many of those planets have a moon? And I like to argue that you have to have a moon to have life, is that the moon gives us a tidal pool, the tides. The tides on our planet is driven by the moon, and tidal pools, I think, are intimately important for generating life on our own planet. And so, of these 17 billion planets, how many of them have a moon? I don't, that's going to be important. So this is a key science question for the future. The National Academy of Sciences, we do every 10 years, we ask the National Academy of Sciences to give us an idea of what are the most important priorities for the next 10 years that we should be working on. And the National Academy of Sciences says that the next great observatory after the 2030s should be a giant telescope to go look and detect and image and characterize exoplanets, exo-Earths around Earth-like planets around sun-like stars, in order to profoundly change the way we humans view our place in the universe. And so how do you image exoplanets? You have to block the sunlight in order to see the light that's reflected off of the planet. And one way to do that is with a coronagraph. And so the way a coronagraph works is the sunlight comes in through the telescope into the science instrument. We focus it down onto the detector. And then what we do is we block the starlight with the coronagraph mask, which actually causes diffraction. So we got to go ahead and clean up the diffraction, which then produces a pretty ugly point spread function from the star. And then the Earth light comes in, the planet light comes in, and it passes through and is not blocked by the mask, but we can't see it because the starlight is just so many times brighter. So we have to clean up the wavefront in order to make a nice clean point spread function of the star onto the occulting mask. We need to have the occulting mask block more of the starlight. And what to do is we're called digging a dark hole. And so as we block more and more and more of the starlight, then we can see the planet light that passes around the mask. Another way to block the sunlight, the starlight, and see the planets is with a star shade. And so this is a giant petal. It's like a giant flower that we launch into space and spread out. And then we put it thousands of kilometers away from the telescope, very, very far away. And then when we fly the star shade between the telescope and the star system we want to study, and it blocks the starlight and allows us to see the planets from around the edge of the star shade. And so finding planets around planetary systems is complicated. There's an inner working angle. We cannot look too close to the star because of that. We have to block the starlight. We can't look at planets that are in front of the star because there's not enough light to get scattered off of them. We can only look at planets that are sort of in these regions here to the side of the star that are bright. And we have to visit them several times. We have to see the planets actually move. And so here's an example of some data that was taken from 2009 until 2016 with Hubble. And you can see there's 4 different planets that are orbiting their star. These planets are 7 times bigger than Jupiter and a lot very, very far out from their planet. they've got methane and carbon monoxide in their atmospheres. And then here is the first image of Webb that was taken with Webb's coronagraph that's inside the Canadian instrument. And the star is located here, and here is this planet at different wavelengths, 3, 4, 11, and 15 microns. And this planet's about 6 to 12 times bigger than Jupiter and about 20 times further out from its star than Jupiter is from our sun. So, so what are we looking for in habitable planets? A habitable planet needs to have an interior. It needs to have a magnetic field that can protect it from radiation of solar winds of its star. It needs to have an atmosphere that is not toxic, that has the right things we need: oxygen, nitrogen, whatever. It needs to have a surface that things can grow on, and unless it's a water world, you got nothing but fish. And so, how do we find life? What is life? What do we look for when we find life? Is that we're not going to go look and find little green men. No, what we have to do is we want to go look and see what is it the life does. So those of you that have children, what is it? How do you know that your children are alive? How do you know that they have, what is it that they do that's distinctive? Is that they eat and they poop. So what you do is, in order to look for life, we want to look for metabolic byproducts of life metabolization to make energy. So this is a chart of all of the chemical reactions that happen on our own planet that produce energy for all of the living organisms that exist on our Earth, and their byproducts are water and nitrogen and methane and oxygen and carbon monoxide and carbon dioxide and ammonia. And so those are the spectrum of things we want to look for in order to find life. We're going to look for water, we're going to look for oxygen, we're going to look for CO2. And if we can find methane, methane is a really smoking gun. There's no other way to get methane other than biological processes. Other things of interest might be the red edge, which is associated with chlorophyll, or the blue haze, which is associated with ozone. The other thing that's really important in looking at spectra is looking at the spectra of our atmosphere as a function of time. Our own atmosphere, the spectra of it has changed as a function of time. And so when you go and you do those deep cores, you can see that the ratio of the constituent elements change. Is once upon a time, this planet had no oxygen, and then the cyanobacteria came along and produced oxygen. And so looking at the ratio in a planet spectra will tell us something about the biology that's going on that planet. The other thing that looking at is very interesting is photometric variability. So if you were to look at a planet, an exoplanet, and its brightness never ever changed, it would be sort of like Venus. When you look at Venus, its brightness never changes. It's a planet that's just completely covered by clouds, never changes. So if we see a planet that looks like that around another star, we know something. But if we see that its brightness is varying, we can make assumptions about maybe it has clouds, maybe it has continents, maybe it has oceans as it rotates. And the other thing is, if it has oceans, we're going to look for polarization, because light that gets reflected off of an ocean is polarized, and light that so if you see polarized light, you know that you have a liquid surface. So Webb is going to be, it's 6 times bigger than Hubble. It's going to see, it can see further back in time than any other telescope ever before it. Its diffraction limited performance is amazing, and it's just doing incredible science. I think I heard last week that we already have got 120 peer-reviewed papers out of Webb data already, in the sense that since we started releasing data in July. So what we're July, August, September, we're 3 months in, and we've already got 120 papers that are in publication. And then here's just some pretty pictures. This is an image that was released on my wedding anniversary and my grandchild's birthday, August 4th. Here, this is called the Cartwheel Galaxy, a Hubble image and a Webb mid-infrared and near-infrared. The Phantom Galaxy, this was released by the European Space Agency, of Hubble image again compared to a couple of Webb images in August. And this was, I think, last week. This is a binary system that's rotating around each other and is producing shock waves from the solar winds that's compressing the dust, and as it travels through the dust around that planet. So sorry for the cutoff, and I'm happy to answer his questions.
Okay, thank you very much. It was a beautiful talk, and let's have our applause. And yeah, the floor is now open for questions.